All right, in this video, I'll be going over section 9.3. Section 9.3 is about graphing polar equations. Okay, basically, we will be discussing how to graph various types of polar equations. Okay, I want to start with this definition, polar plane versus theta R plane. Okay, recall that the polar plane is a plane where you take your x-axis to be the polar axis and the origin to be the pole. Okay, in that polar plane, we can mark a point r comma theta, where theta is the angular measurement. So if angle is positive, it is an anti-clockwise angle. You measure the angle anti-clockwise, and if r is negative, it should be a clockwise angle, as we discussed earlier. And then this r is the sign distance from the origin. For example, if r is positive, it is in the same direction as the direction specified by theta. Okay, so if r is positive, this length is the magnitude of r. This length will be the value of the r. If r is negative, of course, you have to go in the opposite direction, and then that length will be the magnitude of r. And then what do you mean by the theta r plane? Well, in the theta r plane, you mark your x-axis to be the theta axis and y-axis to be the r axis. Okay, so now you can mark the same point r comma theta on the theta r plane. What you do is you measure this theta length along the x-axis, because x-axis is now theta axis. So you measure that length theta here, and then r along the y-axis. This height should be r. Here I am, of course, assuming that theta and r both are positive. Okay, if both are positive, this will be somewhere here, the value of theta. Whatever the value of theta, you mark it here, and then you take the value of r, you mark it on the y-axis, and then take the corresponding point. That will be the corresponding point r comma theta on the theta r plane. Okay, so now let's take an example and compare these two planes. Okay, for example, let's graph this this same equation in the theta r plane, on the polar plane, and on the theta r plane. Okay, first on the polar plane, if you graph this r is equal to 4 cosine theta, we know that from theorem 9.8, if you have an equation of this form, of course this equation is in that form with your a value is 2. Okay, notice that here you have 4. 4 is 2 times 2, so the value of a is 2. If that is the case, that will be a circle. Okay, if you plot the graph of this polar equation, you will get a circle centered at a comma 0. A comma 0 means 2 comma 0, because value of a is 2. Okay, that's the circle on the polar plane. What about on the theta r plane? On the theta r plane, if you try to graph this one, what would you get? Remember, r is your y-axis this time. R is on your y-axis and theta is on your x-axis. If this doesn't sound familiar to you, think of this as y is equal to 4 times cosine x, because you can view your theta as x and r as y. You know how to graph y is equal to 4 cosine x using your pre-calculus knowledge. So if you graph that, I will stick to r, okay, r and theta, not x and y. So you will get a graph like this. Okay, this is the same graph, same equation on the theta r plane. Okay, r is equal to 4 cosine theta on the theta r plane would look like this. It will of course continue as theta increases, and on the polar plane it will be a circle like this. All right, let's move on. Now let me identify quadrants in polar plane and theta r plane. Remember, this is the first quadrant on the polar plane, right? This is always the first quadrant. That means angles between 0 and pi over 2. And then this is the second quadrant. That is, those are the angles between pi over 2 and pi. And then this is the third quadrant, angles between pi and 3 pi over 2. And these are angles between 3 pi over 2 and 2 pi. Okay, that's the fourth quadrant. And when it comes to theta r plane, this is the first quadrant. This is corresponding to the first quadrant, because these are the angles between theta and pi over 2. That is corresponding to the first quadrant, because here we have angles 0 to pi over 2. And then pi over 2 to 3 pi will be corresponding to the second quadrant in the polar plane. And then pi to 3 pi over 2 will be corresponding to the third quadrant on the polar plane. And then similarly, this range will be corresponding to fourth quadrant on theta. This range will be corresponding to fourth quadrant on the theta polar plane. Okay. All right. Now visiting back the previous example, this graph of this polar equation on the polar plane would look like a circle like this, with center 2, 0. And this is the graph on the theta R plane. We saw that from the previous example. Okay, I'm just drawing this piece of graph. So this is corresponding to that piece. Okay, now can we compare this graph against this one? Which piece is corresponding to which piece on this graph? Well, look at this graph. Okay, when theta is 0, your point is here, right? When theta is 0, your point is here. Okay, and then when theta is increasing, your point is moving this way, and then it comes all the way up to here. When it comes here, theta is 90 degrees. You should be able to see that, because here is the evolution of theta, right? Angle theta. It is increasing, and when it comes to all the way up to this point, theta will be 90 degrees. That means between theta 0 and 90 degrees, your R is positive. It is a positive number because it's directing in the same direction that the angle is specified. So this is the corresponding piece. When angle is between 0 and theta, your R should be positive, but when angle approaches to when angle is pi over 2, your R is 0, because at this point R is 0. Remember, when your theta is approaching to pi over 2, your R is approaching to 0. That's why this is 0. And then between pi over 2 and pi, that means if your angle is in this quadrant, what happens? Let's say, for example, this is the angle. Then the corresponding points on the graph will be here. That is, your R is negative, right? So that means for angles in this range, your R is negative. That is corresponding to this piece. Pardon me, if angle is in this second quadrant, here the points are in the fourth quadrant. Okay, this piece is corresponding to the angles between pi over 2 and 3 pi, pi over 2 and pi. Okay, so this piece is corresponding to fourth quadrant. Okay, those are the points on the graph. And then what happens next? When your theta moves to the third quadrant, again your R is going to be negative, because in third quadrant angles are like this, but the points are on the other side. That means R is negative. Okay, so that means from pi to 3 pi over 2, your R is negative. So this is corresponding to, but the points on the curve, whenever angle is in this quadrant, your points are on the first quadrant, right? Points on this curve is on the first quadrant. So this is corresponding to the first quadrant in the polar plane. And then finally, when angle is between 3 pi over 2 and 2 pi, that means you are in this quadrant. When you are in this quadrant, your R is of course positive, because if you are in this quadrant, your angle, if your angle is this one, the direction of this ray specified by the angle is this direction, and your R is positive. Points are on the curve, so that is corresponding to again fourth quadrant. This, because this piece is lying on the fourth quadrant in the polar plane. Okay, so this is corresponding to the fourth quadrant. Piece lies in the fourth quadrant. Okay, that explains the relationship between polar plane and the theta R plane. Let's move on. Next, I want to talk about symmetry in graphs. Okay, so let's recall some of the materials from our pre-calculus class. When do we say that a graph is symmetric with respect to the x-axis? Remember, a graph is symmetric with respect to the x-axis if for every point x comma y on the graph, the point x comma minus y is also on the graph. What does that mean? That means, let's say you take an arbitrary point x comma y on the graph, then x comma minus y also should be on the graph. How do you get x comma minus y? By looking at this point. It is the point on the other side, right? The mirror image of this point about the x-axis. It will be somewhere here, x comma minus y. This is the mirror point of that point, x comma minus y. Notice that when you say x comma minus y, first coordinate is same, y coordinate is changing the sign. That means if this is positive, if this is positive number, the corresponding y coordinate of the other point would be a negative number, but first coordinate is same. Okay, so that means, or in other words, the graph is symmetric about x-axis if the upper part is the mirror image of the lower part with respect to the x-axis. Okay, if you view this x-axis as a mirror, this part should be the mirror image of the lower part. If that is the case, we say that graph is symmetric with respect to the x-axis. When do we say that a graph is symmetric with respect to the y-axis then? Well, same thing, right? This time graph should be symmetric about y-axis. One part should be, the left-hand side part should be the mirror image of the right-hand side part. If you give that as an abstract definition, if you define that as an abstract way, for any given point x comma y, can someone complete the sentence? What point should be on the graph? This time it is not x comma minus y. This time it is minus x comma y. The point minus x comma y should also be on the graph. Minus x comma y. Notice that this time y coordinates are same, but x coordinates switch the sign. If this is positive, this has to be negative. Okay. All right, that's the definition of being symmetric with respect to y-axis. And when do we say that a graph is symmetric with respect to the origin? Well, it is a graph is symmetric with respect to the origin if there's an observer at the origin, if that observer sees the same thing in both sides, in all sides, then we say that the graph is symmetric with respect to the origin, or you can define it in your pre-calculus. Whenever a point x comma y is on your graph, minus x comma minus y also should be on your graph. Minus x comma minus y also should be on your graph. Okay, that means this is the point. If you join this, draw a line through the origin and extend that line, you should hit the point on the graph on the other side. Okay, so if that is the case for any chosen point, we say that it is symmetric with respect to the origin. Okay, so in other words, you have an observer here. That observer sees the same image in both sides. If the observer look at this side, you see something, and that observer sees the same thing if you look at the other side. That's what it says. Okay, and then this is an important remark. If a graph in the plane has any two of these symmetries, then it has the third symmetry as well. Okay, that means if you have these two symmetries, it is automatically symmetric with respect to the origin, and if it has these two symmetries, it is automatically symmetric with respect to the vertical axis, so on and so forth. Okay. All right, let's move on. Next, I want to discuss the symmetry in the polar plane. A graph is symmetrical with respect to x-axis if for every point r comma theta on the graph, the point r comma minus theta is also on the graph. Okay, that means if there is a point r comma theta on your graph, then r comma minus theta also should be on your graph. Where is r comma minus theta located? If this point is r comma theta, r comma minus theta is, it should be, let's say this theta angle is a positive angle in the first quadrant, then r comma minus theta is, you have to measure minus theta in the clockwise direction, so it would be the point here, right? So it should be the symmetric point with respect to the symmetric point of this point with respect to the x-axis. Okay, because r is same, both we have r in the first coordinate, and the second coordinate, this is theta, this is minus theta, so it should be this point. Okay, so whenever r comma theta is on the graph, then r comma minus theta also should be on the graph if that is symmetric with respect to the x-axis. Okay, and then when do we say that a graph is symmetric with respect to the y-axis? Well, we say that a graph is symmetric with respect to the y-axis if for every point r comma theta on the graph, the point r comma pi minus theta is also on the graph. What does that mean? That means if this point is on the graph, the mirror image of that point about the y-axis should also be on the graph. Okay, what is this point? If this point is r comma theta, by symmetry, you can write the coordinates of this point. R is the same. If this length is the same as this length, so we can take this to be a positive r length. And then the angle. What is this angle? That angle is exactly pi minus theta, because this angle is theta by symmetry. Okay, so this is the, so whenever r comma theta is on your graph, r comma pi minus theta should also be on your graph for that to be a symmetric graph with respect to the y-axis. And then here is the other definition. A graph is symmetric with respect to the origin if for every point r comma theta on the graph, the point minus r comma theta is also on the graph. Okay, you can explain this also in a similar manner like what I explained here. So that's the definition of a graph being symmetric with respect to the origin. All right, let's move on. Okay, now I want to go over this table which provides you the shape of certain polar functions. Here is the first shape that I want to focus on. If you have a polar equation of this form, either r is equal to a plus or minus b cosine theta, or r is equal to a plus or minus b sine theta, where a and b are some non-zero constants. Both a and b are non-zero. Okay. If that is the case, then we can determine the shape. We can draw the shape of these polar functions, polar equations, by looking at this ratio. Okay, this ratio a comma b, the absolute value of a over b, not a comma b, pardon me, absolute value of a over b. When absolute value of a over b is equal to 1, we say that we have the shape of a cardoid. The shape of a cardoid is this shape. Okay, for example, I take an example, r is equal to 1 plus cosine theta. Notice that your a is 1, your b is also 1. That means a over b, absolute value of a over b is exactly 1. In that case, I'm going to get a cardoid. The shape of this cardoid would be like this. Okay, and then the second shape that we could expect is the shape of a lemicon. That happens when the absolute value of a over b is not equal to 1. Okay, there are three possible scenarios under lemicon. For a lemicon, either you have an inner loop when this inequality holds, and dimpled when this absolute value of a over b is between 1 and 2, and convex shape when absolute value of a over b is bigger than 2. Okay, here is an example for this case. Okay, with inner loop. Lemicon with inner loop occurs when absolute value of a over b is less than 1. For example, I take my a to be a1 and b to be 2. That way, a over b is 1 over 2. 1 over 2 is clearly less than 1. Okay, in that case, you will get a shape like this. This is a lemicon with an inner loop. You say that it's an inner loop because you have this inner loop going on here. And then here is an example of a dimple shape that happens when a over b is between 1 and 2. Okay, in this case, notice that your a is 3, b is 2. So a over b is 3 over 2, which is 1.5. 1.5 is between 1 and 2. So you should have a dimple shape. This is the shape of a dimple shape. This is the dimple shape. Okay, and then final shape is convex shape when absolute value of a over b is bigger than 1. So this is the example I'm taking. As you can see, a over b is 2.5. That is bigger than 2. So you will expect a convex shape like this. All right, let's move on and we continue with the table. And then the next set of tables, set of shapes that we are going to be focusing on is r is equal to a sine k theta. Actually, let me spare this part for a later slide. I will explain this one for the time being. If we have a polar equation of this form, either r squared is equal to plus or minus a sine 2 theta, or r squared is equal to plus or minus a cosine 2 theta with a is not equal to 0, then we say that it's a lemniscate. Okay, the shape of those will be r squared is equal to sine 2. The shape of r squared is equal to sine 2 theta will be like this, and r squared is equal to cos 2 theta will take this shape. Okay, I'll be going over examples of this nature. Okay, now we are down to examples. Okay, so let's go over this example first. Here is the example. Show that r is equal to 4 cosine theta is symmetrical with respect to the x-axis, and that r is equal to cosine 2 theta is symmetrical with respect to the x-axis, y-axis, and the origin. Okay, it has all three symmetries. Okay, while this has the symmetry about x-axis. Let's work on this one. How do we show that this is symmetric with respect to the x-axis? Part A. I'll call this part A. Okay, first part. To show that it is symmetric with respect to x-axis, we need to show that for every point r comma theta on the graph of r is equal to 4 sine theta, we need to show that r comma minus theta is also on the same graph. Okay, remember, symmetry with respect to x-axis means if r comma theta is on the graph, then r comma minus theta should also be on the graph. Okay, can we show that here? Assume that r comma theta is on the graph of this one. Then we have r is equal to 4 cosine theta, right? You plug in this theta for theta and r for r, then it should satisfy that equation. That's what we mean by the point r comma theta is on the graph of r is equal to 4 cosine theta. Now we need to show that this point is also on the same graph. For that, what I'm going to do is I'm going to plug in minus theta in this part and then show that I get the same r as the previous r. Okay, as this r. Okay, let me plug in minus theta, this minus theta angle in that expression. I will get 4 times cosine minus theta. But what is 4 times cosine minus theta? Cosine minus theta is just cosine theta, right? Simple trigonometry shows that cosine minus theta is just cosine theta. That is 4 cosine theta. 4 cosine theta is exactly r. So this is r is equal to 4 cosine theta. Okay, so even if you plug in minus theta for this theta, you get the same r. So that means r comma minus theta is on the graph of this polar equation. Okay, so symmetric with respect to the, let me write it, r comma minus theta is also, this is equal to r. Okay, this is equal to r. R comma minus theta is also on the graph of r is equal to 4 cosine theta. Okay, so symmetric with respect to the, that implies that graph is r comma r is equal to 4 cosine theta is symmetric with respect to x-axis. Okay, that completes the proof. Let's move on to the second part. Okay, what do we have to show in the second part? In the second part, you have to show that this graph is symmetric with respect to x-axis, y-axis, and the origin. By following a similar argument as in this first part, you can show that this graph is also symmetric with respect to the x-axis. Basically, you show that for any given point r comma theta on the graph, r comma minus theta is also on the same graph by following the same exact same procedure. Okay, I'll leave that as an exercise. Symmetry with respect to x-axis exercise. I'll do the second part. Okay, in the second part we need to show that it is symmetric with respect to the y-axis. To show that it is symmetric with respect to y-axis, what do we really have to do? In that case, we have to show that for any point, any given point r comma theta on the graph, r comma pi minus theta also should be on the graph, right? That's when we say that the graph is symmetric with respect to the y-axis. So how do we show that for any given pair r comma theta on the graph, this corresponding point r comma pi minus theta is also on the graph? Well, for that, what I'm going to do is I'm going to plug in pi minus theta in my equation. This is the equation given to me. I'm going to plug in that in. Okay, let me add a page here first. This is the equation given to me. R is equal to cosine 2 theta. So I want to show that if r comma theta is on the graph, then r comma pi minus theta is on the graph. Okay, for that I'm going to plug in pi minus theta in my right hand side. Okay, cosine 2 times pi minus theta is equal to cosine 2 pi minus 2 theta. By trigonometry, we know that this is just cosine 2 theta. But cosine 2 theta is exactly r, because r comma theta is on the graph. If r comma theta is on the graph, this point should satisfy this equation. That means r is equal to cosine 2 theta. So this cosine 2 theta is nothing but r. That implies that r comma pi minus theta is also on the graph. Okay, this implies that r comma pi minus theta is on the graph. Why is that true again? It is true because when you plug in this angle in the equation, you get r is equal to cosine 2 theta. Or in other words, when you plug in this angle for theta, it satisfies this equation. Okay. Okay. So this implies that it is symmetric with respect to the y-axis. Symmetric with respect to y-axis. Okay, earlier your exercise was to show that it is symmetric with respect to x-axis. Now we showed that it is symmetric with respect to the y-axis. Now how do we show the symmetry with respect to the origin? Well, since we have two symmetries, the symmetry with respect to the origin is automatic from the previous theorem that we discussed. Remember this theorem? According to this theorem, if a graph in the plane has any two of these symmetries, then it has the third one. Okay, so we have the symmetry with respect to the x-axis, symmetry with respect to the y-axis, then it should be symmetric with respect to the origin as well. This implies that graph is symmetric with respect to origin by theorem. What theorem was it? 9.10. Okay, that completes that one, that example. Let's move on. Next, I want to go over this example. Graph the polar equation r is equal to 1 plus cosine theta. Remember from the table, the shape of that was like this. But let's see how to draw it actually, creating a value table. Okay, so here is what I'm going to do. Notice that this is a periodic function with period 2 pi. So I'm going to and period 2 pi, and also notice that this is symmetric with respect to x-axis, because you can easily show that if r comma theta is on the graph, r comma minus theta is also on the graph. To see that, all what you do is you plug in minus theta here. If you plug in minus theta, it is 1 plus cosine minus theta, but cosine minus theta is just cosine theta. So that means it is the same thing as 1 plus cosine theta, which is equal to r. That means r comma minus theta is also on this graph. That means this is symmetric with respect to the origin. Okay. It is clear that graph is symmetric with respect to x-axis. Okay, that means if we can draw the graph shape of this polar equation on only on the upper half plane, only on this region, then by symmetry we can draw the lower half of the graph, right? So all what we need to do is to consider theta values between 0 and pi on this region, in this region. Okay, if you can consider the theta between 0 and pi, then for other theta values we can easily get the shape of the graph by symmetry. Okay, so for that, let me consider only theta values between 0 and pi. Okay, so when I pick my theta values, I pick values that are familiar to us. What do I mean by familiar to us? Familiar to us means I should be able to find the cosine value, sine value without a calculator. Okay, we know the cosine value of pi over 6 without a calculator, and we know the cosine values of all these angles how to calculate those cosine values without a calculator. Okay, so I take these angles for theta to construct my value table, and here is r. To compute r, you plug in this theta in the function r. Okay, r is equal to 1 plus cosine theta. You plug in theta is equal to 0 here to find the first value, that will be 2, and then you plug in this angle here, so on and so forth. That will give us a set of coordinate pairs. These are the set of coordinate pairs. Okay, now I'm going to mark those coordinate pairs. 0, 2. 0, 2 is clearly here. Pardon me, it should be 2, 2, 0, because r is 2, and theta is 0. This is the point. And then r is 1 plus the square root of 3 over 2, and theta is pi over 6. That will be this point. That will be this point, and the next point will be this one, next one is this one, so on and so forth. You mark all those points. Now you can draw this rough shape of that graph in the upper half plane. Okay, since you know that this graph has to be symmetric with respect to x-axis, you should have the lower half like this. I cannot, of course, draw the lower half. This iPad doesn't allow me to draw the full shape, but you will get a shape like this. This is the upper half, and the lower half is symmetric with respect to the x-axis. Okay, the upper half is the mirror image of the lower half with respect to x-axis. So that's how you graph a polar equation of this form. Okay, let's continue our discussion with examples. Next, I want to draw the graph of this particular polar equation. R is equal to 1/2 plus cosine theta. This is called the lemicon. Let's see how to graph this one. Again, notice that this is symmetric with respect to x-axis. Okay, it's clear to see. Whenever r comma theta is on the graph, you should be able to show that r comma minus theta is also on the graph. Basically, you plug in minus theta here, you will see that you get the same function, 1/2 plus cosine theta. That means r comma minus theta is also on the graph. So it is symmetric with respect to x-axis. Okay, symmetric with respect to x-axis. Now I'm going to construct a value table. Okay, again, since it is symmetric with respect to x-axis, it is enough to consider the angles only on the upper half plane. Okay, that is from 0 to pi. Okay, so here is my table again. I take the same values that I used earlier for theta. These are the theta values. Now I compute corresponding r value by plugging the theta value in this function. Okay, so r, if you plug in theta is equal to 0, r will be 3 over 2, so on and so forth. Now I can use these coordinate pairs to mark points. Okay, if I use those coordinate pairs, I will get a set of points like this. Okay, now I join these points with a smooth curve to get my shape. Okay, now since I know that my graph is symmetric with respect to x-axis, I take the mirror image of this piece. I'll get a shape like this, or namely I get this shape. Okay, the upper part is the mirror image of the lower part. Okay, that is because of the symmetry with respect to the x-axis. Okay, that completes that example. Next, I want to talk about how to graph polar equations of this form. R is equal to cosine 2 theta. Okay. Again, we know from let me mention that if you graph this one, you are going to have 4 leaves. Okay, like this. One of these pieces is called a leaf. Okay, altogether we have 4 leaves here. So if you graph this one, I'm giving you the graph first, okay? Then I will walk you through the steps. One of these pieces is called a leaf, and altogether we have 4 leaves, okay? So we can determine how many leaves you are going to have by looking at this equation, okay? In the next table, I will summarize that. To graph this, so since we have 4 leaves for this equation, it is enough to consider the angles between 0 and pi over 2, okay? If you can figure out the shape of this graph in a one quadrant, then by symmetry we can draw the graph. We can complete the graph, okay, by using the symmetry. Okay, this is symmetric with respect to x-axis, y-axis, and the origin. That's something that we showed earlier. Okay, remember in this example we showed that it is symmetric with respect to x-axis, y-axis, and the origin. Okay, so if we can figure out the shape of this one in a one quadrant, that is when theta is between 0 and pi over 2, we can figure out the shape of that on other quadrants. Okay, so here is what we are going to do. We are going to take theta values between 0 and pi over 2. You pick these values so that you can compute 2 theta. Okay, if you plug in these values, you can compute the value of 2 theta. For example, if you plug in pi over 12 here, it becomes pi over 6. You know the value of cosine pi over 6. And if you plug in this value here, you get cosine pi over 4. You know the value of cosine pi over 4. Okay, so on and so forth. Okay, now if you find the corresponding R values, you will get these values. Now you are set to go. Okay, so you are set to draw your graph. With these coordinate pairs, you can draw the graph. When theta is 0, R is 1. That means this point should be on the graph. When theta is pi over 12, R is square root of 3 over 2. It is somewhere here. And then this point, this point, this point, this point, this point, this point, this point. When R is when theta is 3 pi over 2, when pardon me, when theta is pi over 2, your R is minus 1. Notice that this point is minus 1 comma 3 pi over 2, but it is the same point as minus 1 comma pi over 2, because when you take pi over 2 angle is here. If your R is negative, you have to go in the opposite direction, 1 units down. Okay, so this point is the same as minus 1 comma pi over 2. Mark these points 1 comma 0, R is 1, theta is 0 here, and then pi over square root of 3 over 2 comma pi over 12, and so on and so forth. Okay, you will get a bunch of points like this. This point is minus 1 comma pi over 2. Okay, pi over 2 is of course a positive angle like this. Since R is negative, you have to go in the opposite direction. Okay, so this will be minus 1 comma pi over 2. So now all that remains is to join these points with a smooth curve. Okay, if I join these points with a smooth curve, you will get a shape like this. Okay, since this graph is symmetric with respect to since this graph has all the symmetries, it is symmetric with respect to y-axis, so there should be a piece like this, and then there should be a piece like this, there should be a piece like this, and there should be a piece like this, and this is the shape. Okay, if you do that, this is the shape that you're going to get. Okay, the way it is moving when angle is increasing, the way the graph is moving, a point on the graph is moving is this. This is the trace of the graph as theta is increasing. Okay, all right. Okay, now let me look at this table. I will draw the same graph using this shortcut now. Okay, I'm going to show you a shortcut to graphs of that form. Okay, so here is the form that we'll be looking at. R is equal to a sine k theta, or R is equal to a cosine k theta. Okay, we are considering two cases, when k is even and when k is odd. K is even means this coefficient is even. Okay, so when that coefficient is even, when that coefficient is odd. Okay, in the first case, when k is even and when you have a sine function, then the number of leaves will be 2 times k. K is this constant. Okay, and then the first leaf is going to be at 90 divided by k. Okay, first leaf is at the angle 90 divided by k. The space between two leaves is 360 divided by 2k. Okay, and then when it comes to cosine, in the even case, number of leaves is still 2k. It is the same as in the sine case, but the first leaf is at the angle 0. The space between two leaves will be 360 divided by 2k. Okay, in the odd case, when you have sine, the number of leaves is just k, just this coefficient k, and first leaf occurs at 90 over k, and the space between two leaves is 360 divided by k, and number of leaves will be in the case of cosine, the number of leaves will be k, and the first leaf occurs at angle 0, and the space between two leaves will be 360 over k. Okay, so with this table, it is very easy to graph functions of this form, follow functions of this form. Okay, so let's do some examples. Here is the first example I want to do. Okay, let's do the graph of sine r is equal to sine 2 theta and r is equal to cosine 2 theta. Okay, side by side. This is r is equal to sine 2 theta. Here we will draw r is equal to cosine 2 theta. Okay. Okay, now can we find the number of leaves for r is equal to sine 2 theta and cosine 2 theta? Notice that in both cases we have 2, 2. That means k is even, right? That means we are in this column. K is even. Okay. In both cases, number of leaves is given by 2k. Okay. 2k means here the value of k is of course 2. 2 times 2, which is number of leaves is 2 times 2, which is 4. Here also number of leaves is 2 times 2, which is 4. Now, where is the first leaf? In the case of cosine, always the first leaf is at angle 0. Okay, first leaf is at angle 0 in the case of cosine. 0 degrees. Okay, when I say 0, it's 0 degrees. In the case of sine, where is the first leaf? In the case of sine, the first leaf is at 90 divided by k. K is 2 in our case. So it is 90 divided by 2, which is 45, or pi over 4. Okay, and then finally space between two leaves, that will be 360 over 2k for both graphs. 360 over 2k, that is 360 over 2 times k. K is 2. What is this? Pi over 2. This is also pi over 2. Okay, now we have figured out the first leaf. First leaf is at pi over 4, and space between two leaves is pi over 2. Okay, so let me draw the first leaf. First leaf is at let's deal with the sine case first. This is where you have, okay, this is where you have the first leaf, because first leaf is at pi over 4. This angle is pi over 4. Okay, this is where you have the first leaf, and then the space between two leaves is pi over 4. So every pi over 4 you have a leaf. Okay, here is the first leaf, and if you go pi over 4 you have another leaf, and if you go another pi over 4 from there, pardon me, pi over 2. Space between two leaves is pi over 2. If you go pi over 2 from here, you will land somewhere here, so you are going to have a leaf there. And if you go another pi over 2 from there, you will have a leaf here, and then another pi over 2, you will have a leaf there. As you can see, you are going to have 4 leaves, as the first line suggests. Okay, so let me draw these lines. This is the second leaf, this is the third leaf, and this is the fourth leaf. Okay, now it's all about drawing the graph. Okay, we know that this is the first leaf. How do you start? Okay, you start with angle pi over 4, and then as you move, you will get a shape like this. And notice that the r, when angle is pi over 4, r is 1. If you plug in pi over 4 here, you get r is equal to 1. That means you will get a shape like this. Pardon me. Let me draw it like individual leaves. Okay, these are symmetric. Okay, my drawing is not good. This is the same as this one. Maybe I will redraw this one. It doesn't look good. Okay, so that will be the graph of sine. Okay, make sure that this length is 1. That's because when you plug in theta is equal to pi over 4 in this equation, you will get r is equal to 1. So this should be 1. It should be 1 for all these leaves. Okay. All right. Now, if you want to see the evolution of this curve, how this curve is moving as theta is increasing, remember this is the starting leaf, right? Leaf. So if you start here, you will see that it is moving like this. And it will come like this, and it will come back to the starting point. Okay, now let's move to the cosine case, other graph. For other graph, we know that the starting leaf is 0. So that means this is going to be there's going to be a leaf on that polar axis, and space between two leaves is pi over 4. So I go pi over 4 from this leaf, I will land here. So second leaf will be here. Let me use the color. Second leaf will be here, and third leaf will be here, and the fourth leaf will be here. Altogether we have 4 leaves, as this suggests. Okay, now it's about drawing. You can draw symmetric leaves like this, and make sure that this length is 1, because when you plug in theta is equal to 0 here, that is cosine 0. Cosine 0 is 1. Your r is 1. Okay, similarly here should be like this. By the way, this should be symmetric. Okay, my drawing is not the perfect, and then you will get final leaf like this. Okay, so if you look at the evolution of these points, when theta is equal to 0 here, when theta is increasing, it will be going like this. Okay, it will come back to the point where you start. Okay, so that's the shape of r is equal to cosine 2 theta. Okay, that completes that example. I want to go over another example of that type, this time with odd coefficient 3, 3. Both we have sine and cosine, but with odd coefficients. What is the number of leaves in this case? In the odd case, if you go back to the table, this is the column corresponding to the odd case. In both cases, number of leaves is k is 3, so the number of leaves is 3, 3. And first leaf, for the cosine case, the first leaf is going to be at 0. For the sine case, it is 90 over k. This is going to be 90 over 3, that is pi over 6, right? 30 degrees. Here it is 0. In the cosine case, always the first leaf is 0. Now, space between two leaves would be 360 over k in both cases, when k is odd. Okay, 360 divided by k. 360 divided by k is 3. 360 divided by 3. So what is this angle? Well, 120, right? That is 2 pi over 3. This is also 2 pi over 3. Oh, okay, let's start with this starting angle, which is pi over 6. Pi over 6, say somewhere here. And then every 2 pi over 3, or in every 120 degrees, you are going to have a leaf. So I'm going to measure 120 degrees from here. So that should be somewhere here. You're going to have a leaf here. And then in another 120 degrees, you're going to have another leaf that should coincide with this vertical axis. Okay, the other leaf is here. Now we can draw the graph. Okay, as you can see, we get 3 leaves. 1, 2, 3. Now it's all about drawing the graph. You will get a shape like this. Okay, that completes that part. And then what about part 2? R is equal to cosine 3 theta. Again, we are going to get 3 leaves. Starting leaf is at 0. So here is where you have the starting leaf. This black color. So here you have a leaf, and then in every 120 degrees, you are going to have a leaf, right? That means you are going to have a leaf here, and then you will have another leaf here. Okay, so now it's all about drawing. Let's go ahead and draw the graph. You will get a shape like this. Okay, with 3 leaves. So that completes that example. Okay, let's move on, and we are down to the last example of this section. We are going to draw a lemniscate. Okay, so shape of lemniscate, and as you can remember, this is an equation that we saw earlier in the table that I introduced. Okay, so let's see how to graph this one. Okay, first of all, we are going to make some observations. The observations that we are going to make is this graph is symmetric with respect to the origin. Actually, before that, notice that this theta values, you cannot have theta values between the third and fourth quadrants. Why is that? When theta is in the second quadrant or fourth quadrant, this is the second, fourth quadrant, notice that this value is going to be a negative number. That's not possible because r squared, square is always a positive number, right? Or the worst case scenario is 0. So you cannot have negative numbers here, okay? Because you have r squared here. So you need to make sure that you don't plug in, take theta values that would make your sine to theta negative, okay? In these two quadrants, in quadrant 2 and quadrant 4, you can easily see that from trigonometry, this sine to theta is negative. If you plug in any value in these two, any angle in these two quadrants, so you avoid these two quadrants. So the only angles that we need to worry about is between angles between 0 and pi over 2 and pi over 2 and 3 pi and 3 pi over 2. Okay, these are the angles between pi and 3 pi over 2. So these are the two regions that we need to take care of. Okay, so but also notice that, let me put a right mark here. These are the two quadrants that we'll be focusing on. Now also notice that this graph is symmetric with respect to the origin. Okay, to show that a graph is symmetric with respect to the origin, if you take any point r comma theta on the graph, you need to show that minus r comma theta is also on the graph, right? Or in other words, if you go through the origin and extend a same distance as the magnitude of r, let me make it a little bit shorter here, that point should also be on the graph. Okay, so that means we need to show that this point Can you give me a label for this point? This point is same as r comma pi plus theta, right? R comma pi plus theta should also be on the graph, because if this is theta, this total angle will be pi plus theta, and I take r to be in this direction, so that will be r comma pi plus theta. So if r comma theta is on the graph, we need to show that r comma pi plus theta is also on the graph in order to show that it's symmetric with respect to the origin. Okay, there's a point here. Why I am showing it is symmetric with respect to the origin? Well, first let me show that it is symmetric with respect to the origin. For that, I'm going to plug in pi plus theta in my equation and show that I'm going to get the same r. Okay, and I assume that r comma theta is already on the graph, so that means I already have r squared is equal to sine 2 theta. That's because my point r comma theta is on the graph of this equation, so it should satisfy this equation. Now I'm going to plug in this angle for theta. I'm going to replace my theta by this angle. Then I get sine 2 times pi plus theta. This is equal to sine 2 theta. You should be able to see it. Okay, sine 2 theta. Using simple trigonometry, you should be able to see that this is sine 2 theta. But sine 2 theta is just r squared. What does that tell you? That tells you that this point r comma pi plus theta is also on the graph of this polar equation. Okay, that means it is symmetric. The graph is symmetric with respect to the origin. Is symmetric with respect to origin. Okay, so if you have a shape like this, then you should have the mirror image of that on the other side, okay, with respect to the origin. So all what you need to do is you need to graph this equation only for theta values between 0 and pi over 2. Once you graph that, once you figure that shape out, the other shape is the mirror image of that. Okay, you complete the shape on the other side using the fact that the graph is symmetric with respect to the origin. Okay, so let's make a value table for this one for theta values between 0 and pi over 2 then. Okay, so that's what we are going to do next. Okay, let's go ahead and create a value table for this one for theta values between 0 and pi over 2. Okay, so here is my value table. Theta, I'm picking my theta values to be 0, pi over 12, pi over 8, pi over 6, so on and so forth. And then I compute the corresponding r value. Okay, notice that these values are picked so that if you compute 2 theta for that corresponding theta value, that value should be a familiar angle. What do I mean by familiar angle? You should be able to find the sine value using the trigonometric table without using a calculator. Okay, for example, if you plug in pi over 12 here, you get pi over 6, right? 2 times pi over 12, pi over 6. You know the value of sine pi over 6 using the table. Okay, so you pick those values appropriately. Okay, now you find the corresponding r values by plugging those numbers, by plugging those angles in this equation. Okay, so these are the r values. Now I'm ready to plot the graph. Okay, so now for each of these angle, I have r value, so I can plot these coordinate pairs. When r is equal to when theta is equal to 0, r is equal to 0, so that means it is this point. The next point is r is square root of 2 over 2 and angle is pi over 6. It is this one. The next point is this one, so on and so forth. Okay, so you will get a shape like this. Okay, now but remember, we already realized that this graph is symmetric with respect to the origin. Then if you have a piece like this, there has to be a piece on the other side like this if it is symmetric with respect to the origin. Okay, so the graph would look like this. Remember, you don't have any piece on these in these areas, because when theta is between 0 and in these quadrants, there is no real r value. Okay, r is negative, it's not possible. pardon me, your r squared should be positive. So r squared is not positive when theta is between, theta is in the second quadrant and the fourth quadrant. So there is no piece of the graph happening in those two quadrants. So this completes this example, and with that we conclude that section as well. I will stop there, and I will see you next time.